Greetings, physicists. This lecture will begin our series on objects that rotate. We'll call them angular quantities because they all have to do with some angle. And so let's start with an idea that we have a rod, a non-bendy rod, called rigid rod, and we're going to nail down its left piece here. So it cannot, that piece can't go anywhere, but the right end is free to move. And we're going to make it rotate. And it's going to rotate around like this until it's up here. And so it rotates through some angle theta. And let's put some points on that rod. We'll put a point here and a point out here, and those points rotate to here and they rotate to here. Those points have a displacement. If we were to look at where this point moves, this point here moves across an arc, and that's some distance delta x. And this one here moves across a larger arc because he's farther away. Okay? So that's delta x1 for point 1. We'll call them point 1 and point 2. This could be delta x2. Sometimes you will see notation for these. Instead of delta x, they use S2 or S1 for arc length. That's also common. But regardless of the arc length that they rotate through, they both rotate through the same angle theta. No matter how far away you are from the center of that circle, you rotate the same theta. And so when we discuss objects that rotate, it will be very useful for us to notate them in terms of their angle rather than in terms of the arc length, because the angle is the same for all the points on that rod, assuming of course that this is not a bendy rod. If this rod bent and changed its shape as it rotated, then of course you can get different angles. So we'll say for a rigid rod rotating about an axis, all those thetas are the same. So what we're going to say is that if this was a linear problem, our variable would be delta x. But because we're going to consider the change in angle, we'll call this an angular problem, a rotational problem, and we're going to measure the displacement actually as a delta theta, the change in the angle. And so let's define then, this is position 1, well that's like theta 1, and then it rotates over here, and that is position theta 2, and if you take final minus initial, theta 2 minus theta 1, you get this delta theta. And the way we'll measure theta is in terms of the unit circle. So for the unit circle, if you remember, you start it here and you go around, and positive direction is considered counterclockwise. So a position up here would be 90 degrees, positive 90, and a position over here would be positive 180, etc. So that's for theta. Now, it will also be useful in this unit to use a different, in this section, in this angular quantities section, we're going to talk about other units besides degrees. So let's go draw another arc. So we have this angle here, this position has been at theta. And if we draw a point on that line, again, maybe this point that rotated from here to here and has an arc length S, how would we find that arc length S? Well, an arc length S essentially depends on how far out you are. It depends on, here, let's go this way. If you were this little tiny arc here for the same theta, you would not be as large as if you were out here. So what we'll say is that it depends on this distance, where that arc starts. In other words, the arc length is dependent on the radius. So we will say that the theta is equal to the arc length divided by the radius. So the longer the length, the longer the radius, but that ratio is equal to the theta there. And if we rearrange this, we get the arc length is equal to the radius times the angle. The angles are not changing for each of those radii for a given theta, but the r is getting larger. And so we're going to define this this new unit that r, this radius here, was measured in meters. The r is a linear quantity, right? Up here, if you look at r, this is a straight line. But if we look at s, s is an angular quantity. So we're going to give s its own unit, and that unit will be radians. We will measure s in radians. Now, radians confuses a lot of people, but it's actually a very simple concept. If you took a circle like this and took a radius r, r is some linear distance. Make r some angular distance. Let's say r is a 1 meter radius. Well, let's say I go around the circle a distance. Let me do this in red. Let's say I go around the circle a distance of 1 meter along that arc. I have gone 1 radius worth of distance around that circle. So 1 meter is literally 1 radian. A radian is just a radius worth of that circle. And if you go to a smaller or a larger circle, or let's do a smaller circle because I have no room on this page. But let's say I have a circle whose radius is 1/2 meter. Well, then 1 radian around that circle would be 1/2 meter. That's all a radian is. A radian is an arced length around that circle equal to the radius of that circle. But that also means it's a specific angle, right? In both of these cases, a radian is the same angle because all circles have that same ratio, right? They all have, what, 6 point something? If you were to go around the outside edge of a circle, that distance is always like 6.28 radians. Always, for any circle, no matter how big the circle is, the distance around it is equal to 6.28 times its own radius. Or 2 pi, right? 2 pi radians. That's where that came from. Okay, so that's our notation here. So we will say that s equal to r theta, where r is in meters, theta is in degrees, and s is in radians. All right. So let's keep going from there. We now have this idea. That's how we're going to measure our distances. And so let's say we have the same rod. We have that rod here, this point, and it's going to rotate through some angle. Pretend I didn't draw it getting bigger. There it goes. It rotates through some angle theta. And it does it in a certain period of time. Some delta, I did delta s, but I wanted delta t. Okay. It rotates through this arc in a time period delta t. So its linear displacement would be like a delta s, but we want its angular displacement. So we'll say that its change in position, angularly speaking, was delta theta, and we're going to divide that by how much time it took, delta theta over delta time, position versus time. And that's how fast it was moving. Well, we're going to define that as its angular speed, and we're going to give it this Greek letter, which looks like a W, but I promise it's a Greek letter, omega. So omega, the angular speed, or the average angular speed, will be equal to the change in angular position, theta, over the change in time. And that's just going to be our definition there. And if I want, I had before s equal r theta, right? Which may seem more familiar to you if I read it like this. Delta s is kind of like a delta x. It's a linear distance along an arc, would be equal to the radius times the delta theta. All right, well, what I can do then is I can make a substitution if I divide by r on both sides. I can get that a delta theta equals x over r. make sure I have that right. So I can say that the omega should be equal to, instead of delta theta, I'm going to do delta x divided by r, and then a delta t on bottom. I'm going to move the r to the other side. I'm just going to multiply it. Cancel out here. So look what I'm getting. I'm getting that r omega equals, and this is just delta x over delta t. Well, that's a linear velocity. So that's a delta v. So essentially what I can say here, like before I had delta x, right? Delta x, the linear displacement, was equal to r times the angular displacement. Well, here I can write the same thing, only with velocity, so that the delta v should be equal to the r, the radius, times the delta omega. So this is a way that you can convert linear quantities to angular quantities. Now we're going to make one more definition. Our last definition is going to be the definition of acceleration. And so we will say that if you want to change an angular velocity, you could go from a smaller to a larger angular velocity, or larger to smaller, whatever. You can do that in a certain time period. That's how quickly you're accelerating around a circle. Well, we're going to give that another Greek letter. So instead of a, we're going to give it the Greek letter alpha. So an alpha should be equal to a delta omega over a delta time. But let's imagine this then. A delta omega would be a delta v over a delta r, right? So let's plug that in, and let's make another equation. You could probably see where this is going. So if an a was equal to a delta omega over delta time, that's equal to a delta v over an r delta t, right? Well, delta v over delta t is an acceleration, is a linear acceleration, and I just have to multiply that r to the other side. So what I would get is a linear acceleration, a, should be equal to an r times an angular acceleration, alpha. And I wrote deltas in here, but this works for single quantities as well. So we're going to come up with a couple sets of equations here. These are the linear equations. Delta, well, let's do it this way. Erase, erase, erase. Stop. There we go. We will have constant velocity, delta x, over delta t, constant acceleration, delta v, over delta t, or average or constant. In the angular quantity version, you have omega equal to delta theta over delta t, and you have alpha equal to delta omega over delta t. Now we're going to throw in the conversion between linear position and angular position, which is just x equal to r theta. Then we're going to throw in the conversion between velocity and angular velocity, which is just r omega. And we're going to throw in the conversion between acceleration, angular acceleration, and linear. Oh, I did that backwards. Linear acceleration and angular acceleration. So in all cases, the linear version is on the left, the angular on the right for the conversions. And this should get us where we need to go. Now, you can also use these. Remember we had our constant acceleration equations, right? This is kind of a constant acceleration equation from before, but we had more of them, right? So I'm going to go, let's bring up our constant acceleration equations. We had v equal v naught plus a delta t. We had delta x equal v naught delta t plus 1/2 a delta t squared. And we had v squared equal v naught squared plus 2a delta x. Those were the linear constant acceleration equations. All of those equations actually still apply in an angular format. So let's just write the angular equivalence of them, and you can literally just sub the variables in. So you have omega equal to omega naught plus alpha delta t. That's angular velocity equal initial angular velocity plus angular acceleration times time. You're going to have, instead of delta x, we have a delta theta. The change in angle should be equal to an omega naught delta t plus 1/2 alpha delta times squared. And then we have omega squared equals omega naught squared plus 2 alpha delta theta. So those are the same three equations. All I've done is used the linear versions, or the angular versions of those linear equations. And because it's really just a transposition here, we probably don't have to go back and relearn as much because these are just substitutions. It's just going to take a little practice of recognizing angular format. But solving them is almost exactly the same. And similarly, when we look at graphs, if you remember, in a linear graph of position versus time, this was a constant velocity. Well, if you had an angular graph of theta versus time, this is a constant omega. So the k value, the slope here, was equal to the velocity. Well, the k value here will be equal to omega. If you had a graph of velocity versus time, there were a couple of things. The k value was the acceleration. The area under the curve was equal to the displacement, right? Well, same thing we can do here. If you have a graph of omega versus time, then the k value is the angular acceleration. The slope would be how fast it's accelerating. And the area underneath it would be equal to the change in angular position. So a lot of parallels to our very first unit. All right, so we'll go forward this. There'll be another video on how to solve these things, but this is the general idea of how to deal with rotating objects.